All right, this is the third part of section 4.1, samples and surveys. In this section, we will talk about undercoverage, non-response, wording in questions that can lead to bias. And then also we'll talk about how the sample size, the size of the sample can affect the results as well. All right, so the whole point of sampling is that we use it to infer back to the population, right? So the reason that we sample because we don't have the time or money to do a census to talk to everybody in the population. So we take a sample, hopefully a random representative sample, and then we can infer or draw conclusions about the population. So if I ask 50 Montclair High School seniors if they're going to prom, so long as that sample is representative of the population. I randomly selected it. Then if let's say 40% of those 50 students said they're going to prom, then we would infer that 40% of the seniors at Montclair High School are also going to prom. All right, so the inference is what we call it when we do that. When we take information about a sample and then make a conclusion about a population, that's called inference. And it's one of the most important parts of statistics is the inference. And so why do we rely on random sampling instead of just sampling? You know, we have to have randomness because otherwise we have bias. So we want to avoid bias in selecting samples. If we do, if we randomly select them, then we're less likely to have bias in our results. So the laws of probability allow trustworthy inference about a population. Results from a random sample come with margins of error. So every time I sample, I have variability in my sample. Every time I sample, I'm going to get slightly different results. And so that has to do with this margin of error. Okay, so it gives us a set of boundaries that are the likely error that might result when we do our sampling. And we'll get to that in later chapters. We'll talk about margin of error quite a bit. All right, larger random samples are generally a good thing. So larger n, small n, a larger small n, the bigger the sample size, the more representative of the population the results will be. Smaller samples generally don't do as good of a job. So here's an example. In this example, we talk about like the importance of having a larger sample rather than a smaller sample, so you can see what we typically will see with larger samples. So suppose in theory that we know that 70% of students at a rather large university attended all their classes last week. Now, this is a population proportion, this 70%. And in reality, we're not really going to know this value. So this is all theoretical. But let's assume that we know that 70% of students attended all their classes last week. All right, so now let's assume that we are going to randomly choose 100 students from campus and ask them, hey, did you attend all your classes last week? And let's also assume that they're honest and they answer honestly. And so we would hope that the results, the proportion from the sample, called the sample proportion, or we'll use the symbol P with a little caret above it like we did for predicted Y values. It looks a lot alike, but it's not. It means something totally different. So a little caret above P means the proportion of our sample. And so we would expect that when we ask these 100 people, if the true population proportion is 70%, we would expect that our sample proportion would be close to 70%. And so let's assume that we don't sample like this, but again, this is all sort of theoretical. If we took a sample of size 100 and asked, did you attend all your classes last week? We would expect that about 70% would say yes. because we know the population proportion is 70%. Now let's assume that we did this. We asked 100 people. We got the sample proportion. We took that value and we plotted it on a dot plot, let's say. And then we repeat that. We asked another 100 people. We get the sample proportion, the p hat from that sample, and we plot that value. And we do that again and again and again. And let's assume that we did that 500 times. Now, we never do it like this. It's all theoretical. But what kind of results would we expect to get? And so this is what we would expect to get. We would get some sort of dot plot that looks like this. There's 500 dots on this graph. Each of those dots is one of the 500 samples of size 100. So each one of those dots represents a p hat that we got from a sample size of 100. All right. And so there are 500 dots. Each of those dots are located on an axis that represents its location, represents the p hat or the sample proportion that we got for that sample. So you can see how kind of spread out this data is. We looked at samples of size 100. We asked 100 people, and we would expect don't worry about this, is all computer generated, but this is what the typical results would look like, how spread out. So notice some of the p hats we got were almost down at 55, like 56, and some of them were as high as 83%. Who said they did their homework. So we know that the true proportion is 70. Notice that our dot plot is centered right at 70. But our samples are quite varied. And they're going to vary. In this case, because our sample size is 100, they would vary from about 56 up to about 83% as a result of the results that we got from each of the samples. So they varied quite a bit. The majority of them are right there in the middle at 70, but we do have quite a bit of variety. All right, so what would happen to the distribution of sample proportions? Remember, this is 500 sample proportions. What would that distribution look like if we took a larger sample size? So if instead of a sample size of 100, we did a sample size of 400, notice what happens is that the resulting p hats, the resulting sample proportions are much more closely clustered around the true proportion 70. So when we had sample size of 100, the possible range of values were a little bit wider. And then once we increased our sample size, we quadrupled our sample size from 100 to 400. And then if we were to run again another 500 of those samples, we would get another dot plot. And you can see that the dot plot is much less varied. So the sample proportions we get when we have a larger sample size are much less varied. Now it looks like we're ranging, instead of from 56 up to 83, now we're ranging something like, let's see, 60, I don't know, what is that? It's about 63 up to about 76, right? So they are much less varied. You can kind of hopefully see here that increasing the sample size gives us samples that are much less varied than when we had smaller sample sizes. All right, so what can go wrong when we do sampling? So most sample surveys are affected by errors in addition to sample variability. So we know if we ask 100 people, we're going, we do that again, we're going to get a different result. So we have sample variability. Every time we do a sample, the results are not going to be the same. It's just something that just happens. It's not like we did anything wrong. We are going to get variability in our sample, but we want to make sure that we are reducing our bias as much as possible so that we have a representative sample and the results are representative. So we want to minimize these things. So they're under coverage. This is when certain members of our population are excluded from being part of our sample. So for example, if we're doing a telephone poll, the people who don't own a telephone could not be or would not be able to be part of our sample. So they are eliminated from even being the possibility of being part of our sample. And so that's under coverage. Now, if those people will answer the question vastly differently than those who are part of the sample, then that's going to cause problems. All right, non-response. This is, people who are chosen for the sample get a survey maybe in the mail and then just don't fill it out, like they throw it away, or maybe I've been chosen to be a member of the sample, but my phone number's been disconnected, or they have the wrong phone number for me. So even though I've been elected to be part of the sample, they cannot contact me, or I kind of refuse to participate. All right, so that's called a non-response bias. So a response bias can be from, systematic incorrect answers, for example, when you take a survey. If people maybe aren't understanding the question, they can answer the question in such a way, or answer the wrong question, or they think the question's asking this, but it's asking something else. So my response is going to have bias in it. So that's an issue. And then the wording, it can also be an issue as well. So surveys tend to use leading questions, right? So for example, if a survey question said, knowing that more than 50% of childhood deaths are caused by gun violence, would you support a ban or a more restrictive rules on firearms, right? So most people would be, oh my gosh, that many people are being killed by guns. So yes, I think I would, tend to agree with more strict gun control, for example. So you don't want to have your questions sort of being leading into it. And so often surveys will do this because I'm doing this survey because I want to show that people support gun control. So I'm going to write the questions in a way that get the results I'm looking for. And so that's not valid. That introduces bias. Okay, so your last homework assignment, number 3, so homework 4.1.3 is listed here. These homework problems are due next class.